All right, so our next speaker is going to be Joe Lazio. He's going to be giving us a talk on planets and radio emissions.
Thank you. So the first question you're probably asking is, why am I risking ridicule by showing up at Green Bank with a tie? And this is a classic case of not getting the memo. So actually at JPL last week, people were invited to dress retro in sort of response or in celebration of the Apollo launch and landing. So black, white, but I do not have the fashionably thin black tie, and I substituted the best astronomical equivalent.
But that long hair.
Well, no, if you look at the pictures, right? In fact, yeah, my hair is too long. Right. The second question you're probably asking is, really, planets radio emission? Oh, be serious. So if you go back, well, actually, the reason I'm asking that question is because if you think about what we've talked about to date in terms of extrasolar planets, it's typically been thermal emission. It's either been reflected light from the star, which is typically thermal at the wavelengths people are considering, or it's the actual thermal emission of the star. And if you look at the radio emission, either stellar or planetary, that you would expect from a black body, sitting at, say, 1 AU or a few AU from a host star, over interstellar distances, it's completely hopeless to detect. But if we go back, and one of the neat things about this conference, right, is the looking backward and looking forward. So the Carnegie Institution, back in the 50s, there was this new thing called radio astronomy, and they constructed a telescope, a picture of which you see here on the left, in Western Maryland. In fact, it's celebrating with this plaque from the Maryland Historical Trust, and even though I lived out east for like a decade, I didn't realize that the site was this close. And you see the picture out of circa 1954, so that's kind of, I think it was early days of Gemini, pre-Apollo, operating at this 22 megahertz frequency. And what Ken Franklin and Bernie Burke were doing was they were conducting this observing program, and the well-known Crab Nebula showed up, but they got this occasional interference. And over time, over a few months, they finally figured out, well, the interference is traveling with the stars. It's keeping sidereal time, so it's not tied to a terrestrial source. And at least one of the apocryphal stories is they were out one night, and Bernie was looking. They were out and looking at something, and Bernie says, "Hey, what's that bright thing in the sky?" Somebody else says, "Well, it's Jupiter," and that's when the lights went off. But it took them several months to sort of go from, oh, this is uninteresting terrestrial interference to it's a celestial or at least non-terrestrial source. To a planet. And then, of course, once it was determined that it was a planet, the entire, the field started opening up. So Act 2, or the next step, is, yeah, in fact, planets do emit radio emission, and one of the reasons they emit radio radiation is because it's a non-thermal process, or one of the reasons we're interested in a non-thermal process. So this discovery was also part of an evolution in astronomy. Astronomy, pre-World War II, say, was essentially thermal. It was essentially optical and maybe hints of near RR, but it's the kind of stuff our eyes could see. It was all thermal processes. And in the 50s and 60s, we started to figure out that non-thermal processes are important in the universe. So here you see the planetary radio emission from Jupiter. This was from the Cassini mission. So we heard earlier about Cassini. This was as Cassini was on its cruise out to Saturn, it went past Jupiter. This is time, this is frequency. The colors are on a logarithmic scale, so red is something like 7 times brighter than blue. You can see there's a wide diversity of radiation with a variety of names, kilometric, hectometric. It keeps going up because, the Franklin-Burke discovery is slightly off the chart up to 20 megahertz. And it's highly variable. And in fact, in the case of Jupiter, at least in the case of Jupiter, the rotation period is determined from the radio radiation because it's thought to be, it's pretty sure that it's linked to the internal magnetic field, which is tied deeply as opposed to the cloud surfaces or cloud structures. And then once we got about the Earth's ionosphere, so in the International Geophysical Year, people discovered that the Earth also emits this radio radiation. By the time of at least the Voyagers, Saturn, maybe it was even the Pioneers, Saturn was detected as a radio emitter, and then ultimately with Voyager 2, Uranus and Neptune. These are actually, these are these are spectra. So power or flux density is a function of frequency. Once again, the Franklin Burke discovery is out here somewhere up at 20 megahertz, and you can tell they could detect Jupiter, but they could detect nothing else because this line indicates the approximate ionosphere cutoff. Below that frequency, essentially the ionosphere does not permit much radio radiation to get through, with some exceptions, say in Tasmania. So most of this part of the frequency spectrum can only be seen from space. Now, if we think about an extrasolar planetary perspective, one of the reasons that people could be potentially interested in this is, as I already hinted, the magnetic field is driven by dynamo processes in the interior of the planets. So if the solar system planets are any analog or any guide to nature, what that's telling us is the Earth has a strong magnetic field, and we know it has at least a liquid iron core, or outer iron core. And so it's a conducting, convecting fluid. It sustains the dynamo, and it can generate a magnetic field. In the case of Jupiter and Saturn, hydrogen under sufficient pressure actually turns metallic. So now you have a conducting substance. It doesn't take much convection, and voila, you have, at least in principle, a dynamo being produced. I have the Juno spacecraft, or the Juno mission, represented here because, of course, it's orbiting Jupiter right now. Among other things, it's actually, and I'll show examples, or I'll hint at this later as well, it's going through the polar regions, so it's actually sampling directly where the radio emission is being generated. It's also, one of its prime goals is to inform us about the interior structure by what's called gravity field measurements, or gravity science. And it's already hinting that the structure of the core is much different than what we thought originally. And then finally, Uranus and Neptune, the interiors here are thought to be sort of briny oceans, if you will, or very briny sludges. But again, water can be water, you mix in some salts, it becomes conducting, and then again, you stir it up a little bit, you've got a conducting, convecting fluid. So, and again, if the solar system planets are any guide to extrasolar planets, that's one of the interesting aspects is by determining that there's a magnetic field, you then learn something about the interior structure and the interior composition of the planet. So we've already seen this figure at least once. I think Angie showed it. This is a slightly different version from Leslie Rogers, but here's the planetary mass for extrasolar planets. Here's the planetary radius. Again, the mass, as was discussed yesterday, is from radial velocities. The radius is from transits. So this collection at the time when Leslie put this plot together, these were the planets that were known. And then these curves show you the composition of a planet that's made purely of that substance. So for instance, this is a pure water world. If you were to build a planet out of nothing but H2O, that's the curve that it would represent in this radius mass plane. And so there's some obvious things. So for instance, these planets up here, essentially the bulk densities are such that you have to build them out of hydrogen. There's nothing else that can do it. But you can see as you get down into these more, Neptunes, mini-Neptunes, super-Earths, now the uncertainties become substantial. It's also oftentimes degenerate. So if you mix iron, rock, and water, you can get degeneracies of how you would represent these various planets. These two red, whatever they are, stars or something, represent Earth and Venus. And you can tell they fit nicely on the rock line, indicating they're mostly silicates. But you can also tell there are significant uncertainties. And so one of the ideas is we'd like to be able to do not just bulk density, but we'd like to know something about composition structure and magnetic fields being tied presumably to an interior is potentially a way to do this. The other aspect, and this surprised me I didn't realize this until a few years ago. I didn't bring my analog Boy Scout compass with me, but the Earth's magnetic field has been known since antiquity, right? And yet it's not at all obvious from what we know about magnetic field dynamos that the Earth should have a magnetic field. So there are all kinds of things, and I'm not entirely sure I understand them. There are all kinds of things in which the Earth's dynamo is sort of right on the bloody edge, or right on the bleeding edge of whether it could sustain a dynamo or not. So you do a little bit change to the composition of the core, or somehow change the convection a little bit, and the Earth's dynamo could potentially have either shut down or never exist. And then in the astrobiology context, this becomes interesting because we've actually watched the atmosphere of a planet being eroded by its interaction with the stellar wind. So in the astrobiology context, a magnetic field is often invoked to help protect a planet's atmosphere. This is the Maven spacecraft. It is orbiting Mars now, and one of its goals was to study the Martian atmosphere. And as the sun emits the solar wind, and in particular violent solar wind events known as coronal mass ejections, the Maven mission, or the Maven science team, could actually watch the atmosphere being ripped off it. And so an obvious question you might ask that we can't answer in today's solar system, but had Mars, actually Mars did at one point have a magnetic field, and it shut down. There's still residual magnetism. But if Mars had been able to sustain a dynamo a little bit longer, or was able to sustain a dynamo today, would it have a global magnetic field and therefore be a slightly more temperate planet? The radiation mechanism itself, I've sort of alluded to it. It's driven by both the planet has to have a magnetic field. It also has to interact with the host star's stellar wind. So this is a particularly dramatic example, but if a star puts out one of these coronal mass ejections, this is a plasma moving outward. It interacts with the magnetic field of the planet. You get particles accelerated in the planet's magnetic field. They stream down the magnetic field lines, and we can actually watch this. Two particularly good examples. This is the Earth, so there was an actual spacecraft that was able to do ultraviolet observations. So if you were standing on the surface of the Earth at the time of these observations, say in Canada or something, and looking up, you would have seen the northern lights. So this ultraviolet auroral oval right here are the energetic particles streaming in and then exciting the atmosphere. And then these lines indicate where they were watching the electrons also stream down the magnetic fields. They're gyrating around the magnetic fields, producing gyro radiation. This is the case of Jupiter. These are now HST UV observations, but you can again see the auroral oval. You can see magnetic, I guess with a better point spread function, you can see the footprint point of Io. So there's a magnetic tube that connects Io with Jupiter. And again, along here, not only are there energetic particles that are fluorescing the upper atmosphere and producing this UV emission, but there's radio emission being generated as they come down. And again, the Juno spacecraft is flying right through those regions where it's being emitted, or in fact generated. In an extrasolar planetary the one other thing I didn't mention about this, which is important for this next, when this radio radiation is a cyclotron, so the electrons are gyrating around a magnetic field, but that only works as long as the cyclotron frequency is above the local plasma frequency. So what happens is this shuts off, presumably pretty close to, in the case of Jupiter, near the cloud tops. In the case of the Earth, it's a little bit more complex, but it shuts off, and that gives you a measure of what the planetary magnetic field strength is. And this cutoff is dramatic. In fact, if you were looking at those spectra closely, you noticed all of the planets had a pretty dramatic cutoff in frequency. So what we really like to do in an extrasolar planetary context is do something like this. This is an all-sky view from the long wavelength array at Caltech's Owens Valley. Here's 30 to 43 megahertz. So that's almost overlapping with the original Franklin and Burke observations. And you can see various so-called A-team radio sources and the sun noted. You also see Jupiter. So Jupiter shows up quite brightly here, quite strongly. You go up only a small amount in frequency. Now this is 48 to 78 megahertz. Everything else is there and Jupiter's absent. So it's an exponential cutoff. You go above it, the radio radiation just shuts down. And this is the case, so this is what we can do in the solar system from the ground. What we'd really like to be able to do is, of course, do that for extrasolar planets, and from that then determine the magnetic field strengths. So people have been trying to do this. This is, I think, close to a capture of the state of the field, or a vista view, but these are, as a function of frequencies, the flux density limits that have been put by a variety of telescopes, including the GUT. Again, there's a very close connection between the frequency and the magnetic field strength, so you can map this axis frequency straight into planetary magnetic field strength. There's an interesting, you can sort of hint at an envelope here, which is real, but I won't get into that. If I put Jupiter on this plot, however, and put it out at something like 10 parsecs, it occupies over here. So you can see there are immediate two problems. One is, with the exception of some of the higher frequency measurements, we really don't yet have the sensitivity, or you would expect that we don't yet have the sensitivity unless extrasolar planets surprise us, which they've done in the past, The other thing is, of course, if you take Jupiter as a guide, we really probably shouldn't expect emission much above, say, 50 megahertz, and there have been very few searches above, below 50 megahertz. Now, again, if you talk to theorists, I think Peter Driscoll, among others, has come up with novel concepts of how you could push this emission, essentially the magnetic field strength, to higher field strengths, and therefore the radio emission to higher values. I'm a poor observer, so I sort of say, well, we got to use the telescopes we have or build new ones. And for the moment, my money's on saying that we have to go lower in frequency. The other thing is, of course, this blue bar is the part that can't be observed from the ground. So you can probably see where I'm going with this. Ultimately, this is probably going to take, or almost certainly going to take, some kind of space-based telescope. So I'd really like to take some array, get it off the ground, and just move it up into space. Here's an artist's concept of what that might look like. The actual radio things that are needed are fairly small. I'll show you in a moment a concept, and the radio itself you can hold in your hand. The only interesting thing are these large wire booms that are actually fairly substantial because of the low frequencies and long wavelengths. So what I hope is the first step in this is a concept called the Sun Radio Interferometer Space Experiment. It is a collection of 6 CubeSats that would orbit at GEO if NASA selects it. They're 6U CubeSats, so they're about so big. Again, the radio is actually sort of hand-sized. The booms coming off are 5 meters long for actually detecting the radio radiation to give you an indication of the wavelengths. As the name hints, with 6 antennas, about the only thing bright enough in the sky to see is the sun, or we're pitching the science mission on the sun, although a student project that we've also pitched to NASA is the students at University of Michigan will attempt to detect the Saturnian radio radiation. We stand right now in so-called a phase A study, an extended phase A study, which in some sense is a good thing because it actually ends up meaning that we'll have a launch delay of a year beyond what we initially proposed, which moves us farther into solar maximum, and therefore we'll have more coronal mass ejection events to study. However, going back to something, I guess Catherine was sort of riffing on something Barry Blumberg said, the first concept of something like this, of which I'm aware in the literature, is about 1988. So in some sense, I really consider myself to be sort of second generational in trying to get this project. I was not around thinking about this kind of stuff. And some combination of the science now being right, the technology being there, but it could very well be another generation that actually gets to the point of looking at extrasolar planets. Okay, I'm being warned that I don't have time to talk about the anomalous radio emissions from the planet Earth. I'll just note, actually, there's an interesting poster out there on planetary radar. The Green Bank Telescope participates as a receiver in planetary radar. Let's keep going. Other than to say, it's a reasonable expectation. If you take us and think about could we detect ourselves, a short answer is we should be able to detect ourselves over reasonable distances based, if nothing else, on planetary radar. Transmissions that we're not intending to communicate with other civilizations. There's actually an aspect of planetary defense to it. But it is stimulating to think about. It doesn't take much more than our technology to detect ourselves. So I'll close, going back to the original discovery. Ken Kellerman organized a workshop here several years ago on serendipitous discoveries in radio astronomy. And so there's this nice interchange between Ken Franklin recounts the discovery, and in it he says, every so often when they were trying to figure this out or when they were getting their first observations, he'd say, at some point we should figure out what that interference is. And Bernie's response, you can see, it's like, it's some boring interference, right? It's a boring terrestrial techno-signature. And actually, I think this is one of those cases in which you don't let the truth get in the way of a good story. But there was also this possibility going around the Carnegie lab at the time of, well, maybe this is a farmhound returning from the date. But it is, I think, also an indication, here was a celestial signal, interesting celestial signal that was disregarded because it was assumed to be a terrestrial technosignature. And one of the potential risks, I think, particularly with, these guys were very close to the telescope, actually building it. Jocelyn Bell says one of the important things in her discovery of pulsars was they built that telescope by hand. results. And one of the risks is, of course, that we think we know what we're looking for, and we'll end up tossing out the interesting technosignatures because we think, oh, it's some boring astrophysical. Okay, so with that, I'll conclude. I'll leave the conclusions up and let you ask questions if you have any. I see Charlie. Yeah, I saw Charlie first.
Yeah, Joe, in your simulation of a coronal mass ejection, you showed a planet, and downwind from the coronal mass ejection was a recombination event that looked pretty bright. And I'm wondering if that's a way, how bright is that, and is that possible to be seen? For example, yesterday we heard Meredith McGregor talk about panchromatic observations of a very flaring planet and dwarf, and if it had magnetic planets with magnetic fields close by, and would we be able to see the magnetic recombination that you showed in your simulation? And if you could, maybe that's a time delay explanation. If there is one between the radio and the others.
Yeah, going back to what Meredith, I don't think that I'm a bit maybe outside my envelope here, but I don't think that you would expect magnetic reconnection really to give you strong millimeter wave emission. People have suggested, I guess the movie's not playing, but people have suggested that, for instance, by looking at when a star flares, you might then be able to do things like trigger potential observations of planets or the response of a planet to the flare from a star.
But how bright is that magnetic recombination event that looked bright in your simulation? Is that just a simulation?
Yeah, this is, I mean, if you're actually thinking, well,
at the fifth slide.
Well, I think maybe the faster way to answer it is, that's the response of the planet
Yes.
to a star.
Yes.
I guess maybe that's a good way to look at it. Here's the response of a planet to a star, and even taking into account variability, unless they're more exotic than Jupiter.
Well, doesn't that outshine the planet's own emission?
Let's take it offline since I see a few other questions.
Would you like to comment on the possible use of putting a radio telescope on the far side of the moon to do extremely long wavelength radio astronomy? Because I hear it's a very good place to be.
You just notice the moon ain't in there. I've done a lot of work on it. At the moment, my betting is that the limiting factors, the common is RFI, and the limiting factors right now don't seem to be RFI. They seem to be other things. It's horrendously expensive to get to the surface of the moon. Staying up in space is much cheaper. Particularly at this point, we're still at the level of small experiments, and we could not afford at a small experiment to get to the surface of the moon.
All right, we have time for one more.
So when do you think we'll be able to detect potentially natural radio emissions from potentially habitable planets?
You heard my comment about third generational. I mean, this thing, sunrise will definitely not do it. It's going to be at least an order of magnitude up from sunrise. Alan, as a Carnegie,
Yeah,
he should get it.
Yeah, I was going to say, he looked very excited. I was going to give him a chance as well.
Thank you for telling the story about Franklin and Burke. I just want to add a few more details from the exam perspective. The story was, I'm not sure about the farm hand returning from the date, but the story is that they thought that this happened in Poolsville, Maryland, which is farm country, and they just thought someone was turning on an engine of some sort, and that was what they were seeing accidentally. But the interesting part of it is that when NASA headquarters got interested in starting the search for extrasolar planets in 1988, they created the Physical Studies Science Committee, and they chose Bernie Burke to be the chair because he had accidentally found a planet, and there wasn't anyone else around who actually found a planet.
Before you get started, I've got to tell you also that I was at a party a few years back and met this elderly gentleman, and when he learned I was an astronomer, he said, you know, when I was a kid, we had this farm outside D.C., and my dad rented this field to a bunch of astronomers from Washington. Did they ever find anything?
All right, let's thank Joseph again. All right, our next speaker is Stefanie Milam, and she will be talking to us about cometary astrobiology.
So I'm going to try to teach you all about cometary astrobiology in 15 minutes, and I assure you that I will fail, because I have a lot to talk about and I get really excited about the topic, but I'll do my best. So here we go. There's a lot of questions, I guess, about why we care about comets, you know, whether or not they're really pristine, what they really mean. You know, there's even jokes about how can lumps of rock zooming around in space affect our lives down here. Well, in a nutshell, cometary impacts are real. They do happen. We've seen a couple of close encounters actually within the last few years. There was a very brief whiff of a comet over the surface of Mars. And actually, about 20 years ago, there was actually a comet that ran into the side of Jupiter. This is actually quite significant because this is distributing volatiles, rocks, organics to the surface of planets or the atmospheres of planets. The question is what does that material look like? Will it survive an impact, especially on a terrestrial body? And you know, how complex is it, and where is it from? Is it actually from within the solar system? Did it form within the comet itself? Is it something, as Ted was alluding to earlier, formed from the pre-solar nebula or disk? But I also want to make sure that everybody understands that we actually fly through comet dust every single year. This is what most of our meteor showers are. So we are getting rained down with comet debris every single time you see a beautiful meteor shower. So this is something that happens real time. And actually comets fragment quite significantly. So this is comet 73P. This comet came around in perihelion and it broke apart the previous passage to the sun. And we actually can follow these fragments, these comet fragments, every single year. Most of them have survived. So we can actually study the composition of each of these fragments. They all look the same, which tells us a lot about what comets are, how they're made, as well as what they're made from. So in a nutshell, there's the idea that comets have some amount of pristine material that's native to when the solar system was formed. And maybe even going back further, as comets were suggested earlier, based on isotope ratios. So if you just think about the life cycle of a star, there's a lot of processing that can actually happen between each of these different steps. Some of them, especially this one going from a disk into a solar system, or even just during the disk itself, there's quite a bit of processing, as was said yesterday and today. So what amount of this material from the interstellar medium, or even, as Sun was saying yesterday, from an evolved star, is actually preserved and then made into planets, or preserved in cometary bodies or small bodies in the inner solar system. So we know that there's a lot of processing that's going on. We know that there's planets going on. We have a limit in capability right now to how much we can actually detect within gas disks, especially as far as their molecular content. We're getting there. Sensitivity is definitely increasing. Surveys are getting larger, and new instrumentation and facilities, some space-based, some ground-based, are coming online that are going to help us get to the answer of this. But it is quite complicated, and it is quite terrifying if you think about volatile organic chemistry, which is what I'm primarily going to be talking about today. There's ion molecule chemistry and photochemistry that happens within the disk. There's migration, there's transportation. These are things that we've known and we've actually been able to study from sample return missions, from the Stardust mission, for example. We see highly processed material from that return sample, as well as volatile material that would not survive such temperatures as being close to the inner disk. So we know there's a significant amount of disk mixing that happens and is preserved within cometary nuclei. So what we're trying to get at is this is this is not all 200, of the known interstellar molecules. This is an eye chart, and this will be a test at the end. I hope you have good photographic memory. If you just squint your eyes, all I want you to glimpse at is that all the white molecules are organic. The interstellar medium is very, very, very organic. And this isn't even including things like PAHs or other solid forms of carbon. the volatile material that we see in space is very organic. And up until Rosetta, comets were also seen as very organic. So this is the list of, a few dozen of the molecules that we routinely detect in comets, especially before Rosetta, what our known inventory was. And all of these are very comparable to what we see in the interstellar medium, both in abundance as well as in composition. But it's not so easy for us to detect 200 molecules in comets. They're very challenging to observe. First of all, your telescope has to be in the right hemisphere. If you are restricted to only nighttime observations, the comet has to be active or in the sky at night. Sometimes we get lucky and we get daytime observations. They're dynamic, they're constantly changing, and sometimes they're dust-rich instead of gas-rich. We have all kinds of complications with us, but we get lucky. Every once in a while we get good comets, and we have more and more sensitive and better capabilities so that we can actually observe more objects. But then chemistry starts coming into question, and I'll get to that in a little bit later in the talk. But we do have the advantage that we do have samples that have been returned from comets, as well as meteorites and IDPs, interplanetary dust particles. And we know that they have very complex chemistry, things like amino acids, all these prebiotic molecules that as an astrobiologist, we're very, very interested in. So connecting this very simple, very organic though, interstellar chemistry to something that could possibly be preserved in the solar system, in objects such as comets or meteorites, for example, how it's preserved and when it turns into this complex nature is a huge question and enigma in cometary science. So the easiest way to do this and get the full inventory, obviously, is to go to a comet. We've been to a few. These are pictures of actual nuclei that we've actually been to. Most of these missions, though, did not have mass spectrometers. Only one, which is the WIL2 81P, we were able to bring sample back. And the rest were mostly flyby missions, except for 67P, which is where we had our Rosetta mission from the European Space Agency. This mission opened the door to organic and bio and astrobiology chemistry to cometary science. We now know that not only do we have this organic chemistry that we can detect remotely, but now from in situ measurements with an orbiter, we could actually discover things like glycine. This is the second comet glycine was detected in. It actually was detected in the WIL2 return sample. Two comets now have glycine, Ted, not one. But we also have all these long carbon chains. We have some crazy molecules. Where's the stinky ones? Where's my skunk? Oh, sulfide-bearing molecules, sulfur dioxide, carbon disulfide. Some crazy ones, argon, krypton, xenon now, hydrogen fluoride, phosphorus, chloromethane. A lot of this stuff we really just don't want to be inhaling, but like I said, we fly through, or we actually orbit through comet dust every year. But we can't go to every comet. We try, but NASA doesn't say we can because it costs too much money. And sometimes they select Titan missions instead of comet sample return missions. Shame on them. But so we're limited to providing ground truths to what we can actually do in situ. So this is where ground-based or remote sensing actually comes into play. But this is good because, first of all, it does give us the ground truth for the flyby missions and things like Rosetta that we've actually gone to, as well as we can study a larger sample of targets. We're not going to just one, which may be unique, it may be an enigma. We can get a broader scope of the actual sample of the population. So how are we doing this today? Comets are actually quite beautiful apparitions. They're nice and bright. And actually the general public really loves them. So it's really easy for us to sell our science, as was kind of discussed earlier today. But there's also a lot that we can learn from it. So one of the most, one of the biggest advances that we've had to date for cometary spectroscopy is broadband spectroscopy. So this is where we have large swaths of spectral capability that So this is the IRAM 30 meter, where you get about 32 gigahertz of bandwidth simultaneously. And by doing surveys like this, now we defeat the purpose of the comet not being in the right hemisphere, whether or not we can tune to multiple frequencies to see different molecules, and we can actually do line averaging so we can detect things like complex organics as well as isotopes. And this has really opened the door for us for cometary astrobiology. My favorite astrobiology story for a comet, I just have to mention it, was Comet Lovejoy, which we've now dubbed the Happy Hour Comet. This was the first comet that we detected alcohol and sugar in. It was led by some French colleagues of mine, and so we actually calculated how much alcohol was produced, and it's about 500 bottles of wine per second. So this, to me, is life, if you can imagine. But in reality, what we do is these silly bar charts where we actually compare our abundances of complex organics. I say complex in an astrobiologist or astrochemist sense. Apologies to the biologists here. But this is really a big molecule for astrochemists. So we sort of compare, star-forming regions, disk, as well as other comets, and see how the abundances may or may not vary and what that may or may not mean. The problem is we're usually looking at this fuzzy picture and not the actual nucleus, because we're looking at the coma as a comet comes into the inner solar system. So my group, mostly between myself and Martin Cordner, have pretty much led all the ALMA observations to date, with the exception of, I think, 2 observations. And we've really actually found quite significant contributions to what these molecules look like in cometary coma, and learned a lot about what we used to think were native species. So things like hydrogen cyanide, we believed, and still do believe, came from the nucleus, so it's a preserved volatile in the comet itself. And what we thought was this was actually the same thing as you'd find for other simple organics, but we were wrong, which was great because I actually had part of this in my thesis. So this was really quite, gratifying to find. So what we found was that some of these molecules look like they actually are following jets and tracing jet activity. Some of them have these clumpy distributions, which suggest that they're formed by some other mechanism. This is great because now we can actually model what that profile looks like from a nucleus distributed source and compared to something that's formed from something else like an organic matrix or a grain. And this is what we call extended sources. This means chemistry is actually happening within the comet and the observations we're making. So instead of, again, coming directly from the nucleus, we now have either chemistry that's occurring, creating a distributed source, or it's coming from some other parent species. Go. We're also walking into the world of James Webb. I'm a James Webb project scientist, so I have to say something about James Webb. We will be launching in 2021 and opening a whole new window of cometary chemistry. What you see here in this green line is what a previous COMET mission had as far as a near-infrared spectrometer. This was the Deep Impact mission. It had a resolution of about 100. James Webb in the near-infrared has a resolution of almost 3,000, so we'll be able to resolve comet species. We can do long-term studies, which will be great to compare to things like disk and see where the ice lines are and compare how the volatiles of things of particular interest for ice lines, water, CO2, and CO, how that will vary as a comet comes into the inner solar system. And we can do things like isotopes. Isotopes are really unique, as has already been discussed. Knowing what the D/H ratio is to see whether or not comets have a contribution to Earth's ocean is something that's been very, very in light's eye for especially the general public, as well as planetary science. But we only have about 2 dozen objects now that have been measured in this ratio, with results that vary quite dramatically from a factor of 2 or 3, all the way down to what actual Earth's ocean is. So future surveys would actually be really quite enabling for this kind of science. But nitrogen is the other anomaly in comets. It is actually enriched by a factor of 2 in nitrogen-15 with respect to what Earth is. And this is a value that we measure in multiple comets from NH2, and basically we always get the same answer. This kind of fractionation actually happens in cold interstellar medium as well. So I'm out of time, so I'm going to leave you with just a few key thoughts and happy to take questions.
Any questions?
It's all clear, right?
I had a question. So about when you did those molecular lines, so was there any salient feature that is different between the cold medium and the comets? I mean, the abundance looked fairly similar to me, but I couldn't read all of the fine print.
Oh, so you're talking about
more
the...
oxygen or less oxygen or what?
Everything so far looks pretty consistent within the errors. We've only been able to detect complex organics on this kind of level in a few comets. Again, we are limited by activity, and in the case of IRM, wind or snow. So we're getting there, but you know, surveys are hard, and we only get 1 or 2 good comets a year that we can actually do these kinds of studies.
So that means that you really can't tell whether the comets were protoplanetary or interstellar medium.
Not yet. Isotopes suggest that it's probably before, but I'm waiting for this chemist to tell me that they can see nitrogen fractionation in the midplane, and they're not doing that yet. Ted.
So my impression is that the nitrogen isotopic composition that's been measured in comets is very different from Earth.
Yes.
So it's even more distinct than,
Yes.
than hydrogen. So
Yes.
Again, this raises the issue about whether comets are a significant deliverer of all
Yeah,
here.
so that comes into the question of if there is a nitrogen anomaly in comets that's so significant compared to things like water, and comets are a contribution of water for Earth's ocean, I think a lot of that has to do with how much nitrogen is actually in the Earth's atmosphere. So a mixing of a cometary impact with that little amount of nitrogen. I mean, these abundances are pretty low compared to water abundances, for example, on comets. I mean, a few % at best. So how that would actually enrich would be, an interesting calculation to do.
Mass balance, yeah.
All right, let's bring Stefanie again. All right, our next speaker is Barry Welsh.
Hi, I'd like to thank the SOC for inviting me to give this talk. I hope you don't live to regret it. For those who have no idea what an exocomet is, well, the last talk was all about comets. Exo-comets are just comets that we discover around other stars. So, exo-comets are actually in the news, believe it or not. This talk's all going to be about detections because I'm an instrumentalist, I'm not an astrophysicist, I'm also a retired instrumentalist. Okay, in the news recently, breakup of asteroids or a comet round observed by Kepler. Some guy giving a talk at the SETI Institute on exocomets. He was devastatingly handsome, so you should watch that on YouTube. There's one in Scientific American recently, Comet Blast Star. So there is some sort of public awareness beginning to happen about exocomets as well as exoplanets, obviously. And can't even pronounce it, the Oumuamua object, whatever it was, as it leaves the system, actually left a trail of gas behind it. So, if you consider a comet as something that leaves a gas behind, then that may have been an exocomet from a different solar system passing through ours. Okay, why do we bother even looking at these things, eh? Well, there was a really old idea in the 1970s by Fred Hoyle and Vikram Singh called Panspermia, which said that the galaxy should be seeded by organics from things like comets, asteroids, planetesimals. This was very far looking because molecules in comets weren't actually discovered till the mid-80s, and this was like beginning of 1970 or so. Fred Hoyle, by the way, is one of my great heroes. He's the guy who came up with the great steady state theory, got it totally wrong because Big Bang won out, but he actually wrote the book on stellar nucleosynthesis. His great thing was, it's better to be spectacularly wrong than boringly right. And of course he was from Yorkshire, which makes him even better. Okay, a recent suggestion about why we should look at exocomets is that there's a thing called the diffuse interstellar bands. Every star that we look at, more than about 50 parsecs away, has these absorption features in them. This is every star. They're called the diffuse interstellar bands, and people for the last 100 years have been trying to say, which molecules produce these or whatever. But in a recent paper by Jean-Loup Berthaud and Rosine Lallemont have said that if you look at the population of the organics in DIBS, that's diffuse interstellar bands, it sort of matches the stuff in the in comets. So it could be that the fuel for comets is picked up in the interstellar medium. In other words, we've got a huge reservoir of molecules out there just waiting to be tapped into. Now, if you believe in the late heavy bombardment, which some people don't, some people do, comets could have brought water to the solar system, to the young Earth. And of course, if you see an exocomet around another star, and that star has exocomets, and the comets are coming in, perhaps they are delivering ice, perhaps they're delivering organics to these exoplanets. And you can see that's a sort of sexy thing to talk about at this conference. Another reason to look at them is that they might provide us with a comparison of all the molecules in the ice and compare that to what we already know about comets in the solar system, which gives us some sort of insight into planetary formation. But which stars have exocomets, and how on earth can you detect them? How do you detect a comet around another star? It's bad enough trying to detect an exoplanet, never mind an exocomet. Okay. As you know, this is basically what cometary spectra look like. You heard all about those in the last talk. Okay, the study of exocomet research started with a star called Beta Pictoris. It's in 1984 or so with the IRIS infrared satellite. They saw an excess in this young star. It's an early type star, A5V star, and they saw, where did all this extra infrared come from? And they came up with the idea that it could only be from a dusty disk. This was your original dusty disk star. And of course they took a picture of it, and there you see the well-known disk, that's the red and the yellow, and of course Beta Pic is blocked out by an imager there. So this sort of started the whole thing off. Well, if it's got a disk, perhaps it's got comets around it, who knows? So fortuitously, some ground-based interstellar medium people said, oh, let's take a spectrum of Beta Pic, see what happens. And when you're an interstellar medium guy from ground-based, you only use two lines. You use calcium-2 at 3933 angstroms, it's in the UV, and the other one you use sodium. They happened to be, these were French people, they happened to look at calcium. There's two great papers there, and they looked at it because they got bad weather one day, they took one the next day, got bad weather, so they had about 5 or 6 spectra, and they thought, well, we'll just add them all together and see what happens. But they said, when they looked at them separately, what they saw was this. Okay, a bit of interstellar medium, circumstellar medium physics going on here. The big trough that you can see there is the stellar line. That's a photospheric stellar line. It's very wide, and the reason it's wide is because Beta Pic rotates fast. Its V sin I, that's the rotational velocity, is about 150 kilometers per second. That's quite fast. So this feature there, that absorption feature, is at 20 kilometers per second, and that's the radial velocity of the star. So what you've got is a disk of gas going in sync with the rotational velocity of the star. But every now and then, on separate nights, you get these extra little absorption features. And so perhaps they saw that one night, the next night it had gone and it had moved. What on earth could do that? So, just to remind you, this is the circumstellar. Okay, that's to do with the disk. And then what we're looking for, these little features here. What are they? Okay, at the time the French were not allowed to call these little features exocomets because they didn't have enough confidence to do so. They came up with the great thing calling FEBs, or falling evaporated bodies. The thing is, where's all this gas coming from? Because an A star, when it forms, within 1 million years or so, just blows off all the gas. But there's loads of gas around Beta Pic. So where's it coming from? It's been continually replenished. We also, later on, you'll see that we see similar things around stars that are much older. So somehow, these stars, their disks are getting continually replenished by gas, and that gas is coming from exocomets. And so the way it works is that the exocomet comes in, and when it gets fairly close to the star on a grazing incidence thing, it evaporates, and that's what you see. You see the gas there. And that evaporating gas, we see an absorption, and then it just falls into a circumstellar ring. So as we say down here, this last thing here, the variable calcium absorption is best modeled by assuming the bodies are evaporating gas as they fall on grazing orbits towards the central star, and there's 32 papers since 1990 by this guy called Hervé Burst, who models this stuff. Okay, but why would a comet suddenly just come towards a star? Well, perhaps it needs a trigger, a gravitational trigger. Where would that gravitational trigger come from? Perhaps an exoplanet. So you could argue that if you see exocomets, you can imply that there must be exoplanets around the star. This is important for A-type stars because radial velocity and transit stuff doesn't work for A stars. They're too bright and they rotate too quickly. So here's a little guide for you. This is me in an observatory on the ground. We look through this disk at the central star. So you see the central bit there. There's your circumstellar absorption. 5 minutes gone and 5 minutes left.
5 minutes left.
Okay. And here, when comets come in, okay, they go around the star, and you'll see them coming at red shifted velocities there. So, what we see towards Beta Pig, and somebody's looked at this thing from, they put together 6,000 observations, okay, which is a lot. You get two types of exocomet, or two types of absorption. You get a broad shallow absorption, which are these here, and they're supposedly associated with depleted volatiles. And the narrow deep ones, which is that one there, are probably associated with the fragmentation of small bodies. So, are there other stars out there apart from Beta Pig? Well, we started a program about 9-10 years ago to look for them. And we used calcium-2 again, and we got time at the McDonnell Observatory. And what we do is we look at the stars on subsequent nights 4 or 5 times, weather permitting, to see if we see any changes. So what we're looking for are changes in the central absorption feature, and we're looking for these little narrow FeB, falling evaporated body absorption features. So what does it look like? Okay, here's a star here. No, it's also an A-type star. It's young, 3 million years old. Here's our first. Notice central absorption, but this little thing here and this little thing there. That's on 4th of November. The next night, you notice this thing here has moved now to here. And we've got a new thing coming in there. This has only happened over a period of 24 hours. And here's the next one. You notice everything's gone. There are no comets that night. And the next one, no comets that night. So we got really lucky. How about another one? Okay, look at the black. I've shaded it for you. These are all on subsequent nights. Notice how the black changes and moves. This is like 3 or 4 times as big as that. Equivalent width there being the number of absorbing atoms. And here on a subsequent night, you've got 2 features coming in. So you don't just get single comets, you may get a swarm of comets, or you may be getting comets that are breaking up. And again, we came back a few years later, same star, and you'll notice things are moving all the time. So this is how we detect them. One last thing here, this is a 49 Ceti, it's a very well-known star. This is a little feature there, not seen, well, it's not seen on those nights, and then a new one coming in there. So you've got to have high signal to noise, high resolution, and you've got to have multiple nights of observations, which is hard to get on a big telescope. And if you want to see, oops, I'll keep going. Oh, I don't think you're interested in this. Okay, Tabby Star. I think you all know about Tabby Star, do you? Yeah? This is the Kepler star whose absorption, whose actual, sorry, its intensity is, as measured, varies by up to 20%. And I believe that you wrote a paper on this, is that right? Yeah? Putting many different mechanisms to why a dip like this is a 20% reduction in a few days. What causes something like that? Well, the astrobiology people, the SETI people came up with Dyson spheres, they came up with this, that and the other, but I think, and it's probably true, that the accepted cause of this could be swarms of very dusty comets coming in on a non-periodic basis. But I'll talk about that. Okay, let me keep going because I've only got 5 minutes left. What we'll do now is... Yeah, okay, we go to this one. This is so much better. Okay, I've only dealt with A-stars. They're like a million, how old's the oldest A-star? They only last for a few million years. So if you find planets around them, big deal, they're not going to have enough time to evolve. So I said, okay, we've discovered 20 out of the 25 exocomets exocomet systems that are known. Let's go to F-stars. Why would we want to go to F-stars? Well, let's take Eta Corvi for a start. It's an F2 star. It's got 2 dust belts around it, and it's thought to harbour multiple exoplanets. So there's a good thing to do. And there's a picture of Eta Corvi from ALMA. It's got the dust disk around there. Looks, if it was looked edge on, it would look exactly like Beta Pic. F-stars are hotter and more massive than A-stars. They have more UV radiation, which might be bad for habitability. However, the age of this star is about 1.4 gigayears. That's plenty of time for a civilization to form and then destroy itself. So, we selected a few F-stars with known emitting dust around them, and they have to have fairly large, for F-stars, rotational velocities. Normally, F-star rotational velocities are quite small, but this one is quite large. And what we found is this. These are 3 nights. This central velocity, this central feature here, I just fit with a model, and the model is the interstellar model. And interstellar things don't change. So on that night it doesn't change, that night it doesn't change, that night it doesn't change. Then, on the last night, so there's the one that doesn't change, there's the one that doesn't change, but where's all this extra stuff here coming from? It wasn't there on the other nights, it's there on that night. Can only probably be exocomet ablated gas. So this is the first detection of an exocomet around an F-star. And so conclusion, detecting exocomets round a star is probably a good indicator that that system may have exoplanets. That's great for A-type stars because it's really difficult to do exoplanet detection around an A-star. At the moment, there's 25 of these stars with debris disks that exhibit this FEB phenomenon. You can see that paper there. However, of course, what do we need? Well, people always say the same things. We need more money, we need more observations, da-di-da-di-da-di-da. What we'd like to do is to sample exocomet systems of A-type stars all the way up to like 400, 500 megayears before they blow up. And that might provide some insights on how and when water organics are delivered to exoplanets through cometary impacts. Thank you.
Can you use these observations to get estimates of the masses of these comets, the size of them?
Yes. Yeah, I deliberately did not put up any numbers because you're at a conference. If I told you the number was 10 to the 52, whatevers, it would just go one ear. I'd give you the paper where the masses of various things that are within the comets, like hydrogen, calcium-2,
Well,
whatever.
larger than Halley, for example, or larger than the ones that we're more familiar with that come into our solar system?
We know that, at least in the case of a few of these exocomets, that the C to O ratio is something like 20 times that we see in the solar system. They're carbon and oxygen rich.
So obviously comets are icy bodies, but I don't tend to think of calcium as being particularly associated with ice in astrophysical environments. So how do you bridge that conceptual gap?
There's calcium, we might as well say that about interstellar grains. That's how the interstellar gas is full of sodium and calcium. That's how the whole study evolved. Exocomets are full of gas. Every time you see a comet, what do you see? You see a tail, okay? And the tail is gas, and the gas has come from calcium thing. The other thing is that it's typically around about 1,000, 1,500 degrees. And this stuff is when, you only see these things when they're very close, within an AU, as they come in and they think. And the reason it's good to study these, because now you see them, now you don't. You never see these again. This is perfect publication stuff, because nobody can possibly argue with it, because they'll never see them again.
But I think, if I can, to answer the question, the sodium, these are the Fraunhofer lines, they're resonant lines, and so the
Yes,
cross
they're
sections are
resonant.
huge. So you don't need a high abundance to see these just stand out.
All right, any more questions? All right, thank you again. Our next speaker is Penny Boston, and she's going to talk to us about extremophile. Is that, wait, yes, that's what it says, okay. Extremophile.
It's extra drippy. So I changed my talk a lot because we've already had several good presentations on various aspects of microbiology and touching on extremophiles and so forth. And so what I've done is select a few things that are particularly potentially important and or problematical, focusing heavily on the problematical. My current job, of course, at NASA is the director of the NASA Astrobiology Institute. I'm going to say only one thing about that up front, but a lot of the work that I will allude to briefly here, of course, was done in my former life as a professor and chair and so forth at New Mexico Tech. And so let me just talk for a moment about Barry Blumberg, dear to many of us. As you well know from Carl's excellent talk on Barry's history, even though he got the Nobel Prize for working on viruses, he himself was not trained as a virologist, and that led to his perception and valuing of interdisciplinarity. So at the time that Barry passed away, he and I were talking about doing some work on viruses in the subsurface. I'm not a virologist either, but it's an area that hasn't been focused on. And even though the NAI has had a focus group in astrovirology for many years, it's been very much on the margins. And people in fields that contribute to astrobiology are essentially not being funded either by NASA or other entities in order to work on real astrovirology questions. And so why do we care? We're not talking about diseases in space here. We're talking about virus-like entities, which could even include prions and viroids and things of that sort, plasmids and whatnot, and their role in evolution on Earth and the prospects for similar types of entities in other biospheres. So they are a major evolutionary driver. And so we are doing the week of September 16th, the dates have not yet been picked, an astrovirology NAI workshop without walls. We invented these things as an institute a number of years ago, and they are very, very useful and very cheap to put on, which is always a good thing. And the website is there, so if you or anyone else are interested in virology, which doesn't just pertain to virologists, it pertains to those of us who are interested in evolution, please let me know or look us up on the website and you'll get details over time. All right, so extremophiles. Obviously, that title, I can't do even a fraction of a percent of justice to this vast field. But the fundamental reason that we care in astrobiology, specifically, is that we have been studying organisms in what people call extreme conditions, hoping that this will help us identify organisms or ways to search for organisms on other planets. Many times, of course, we are dismayed by the tiny size of individual microbes and perhaps overemphasize that, because really on Earth, microbes grow in communities for the most part. Now, sometimes these are very cryptic and hard to detect differences between microbial communities and what one might interpret as a mineral deposit. But they often leave very large, let's see, is this my laser? They leave very large patches of minerally altered materials that they have worked on. Sometimes they chemically transform it in the process of getting energy out of those materials. Sometimes it's actually detoxification, which is probably what went on with this blue item in the middle, because this is copper oxides that are the byproduct of the metabolism of copper sulfides, that microorganisms are splitting the sulfide off and getting energy out of that. So there are many characteristic physical and chemical biosignatures. Okay, so that's why we care. Excuse me. But one of the problems when we try to translate this into space missions, particularly, is we have to decide what kind of life we're looking for. And the reason is because the techniques that we employ to try to fathom whether or not we've got organisms growing in a particular environment and what they are and how to characterize them is exceedingly different from the state-of-the-art and best practices within looking for traces, geochemical and biochemical traces, stable isotopes, and so forth in extinct life. We love to think that we were going to find big fossils, but I think most of us are not holding out much hope for that. So this has significant consequences for who can use what information. Unless we have a biosphere with a lot of extant life in it, it's not going to be useful for exoplanets. And I'm sure if you didn't already know that, you picked that up from other discussions at this meeting. When we come to the extinct life situation, there isn't much hope beyond our own solar system. So looking for traces of life is very nuanced and subtle, and requires, as far as we can tell at this point, hands-on methodologies to actually tackle that. So I made a little list with a few examples. It's much more striking what we don't know about extremophiles. It's really the most of the story. I was tempted to put up one of my usual slides that has a list of all the difficulties that organisms have to overcome, so high and low temperature, and high metals, and high salt, and extremes of pH, and all of that stuff. But I think most people have a grasp of that at this point. But there are things that keep coming up over and over again that we have very flimsy grasp of, and that we argue over, and where our understanding of the actual parameter is fuzzy. And one of these is water activity. The scale of water activity is, if you've got pure water and tons of it, you've got a water activity of 1. All right, so it's easy for you as an organism to slurp it up. So anything below 1 is a much reduced accessibility of the water, and this can be for a lot of reasons. Either the water isn't there, or it's exceedingly briny, or whatever it is. We think that the magic number is 0.6, and I think somebody mentioned it the other day. Maybe Rocco, you mentioned it, I forgot. But we really don't know that that's the lower limit. And one of the other things that is pending in that whole discussion of water activity is whether or not organisms can regularly use water directly from the water vapor phase, or do they have to have it condensed on their surface in some fashion. And people have articles of faith that they bring to bear about this, but the truth is this is an exceedingly difficult thing to study. And it matters a lot in certain very dry environments where water can be transiently in the liquid phase, but is mostly in the vapor phase, and we don't know if they can access it. And there's a lot of fighting over whether a very, very micron, submicron, thin layer of water is going to be adequate for organisms to actually take it in. People make all sorts of claims as to whether that's true or not, and yet, truthfully, show me the research. We don't have it. So, manipulation of the surface, microphysics. One of the striking things to us in our work, largely in the subsurface, is that microorganisms in the subsurface seem to have an extraordinary array of complex surface shapes and things sticking out. We call some of them Smurfs because they have little Smurf hat-like things sticking off them. And a lot of them are fuzzy in very strange ways. And usually when organisms that are in an energy-limited environment are spending energy to make something, it has a function, and we don't know what it is. I suspect that it is a manipulation of the microphysics of the surface, and that may have to do with water, but we don't even know that, right? Multiple tolerances and synergy. So we know that little tiny people, are challenged by all of these circumstances that I mentioned before. We know from a very small amount of research that things like salt tolerance and radiation resistance tend to go together. We don't actually know why. There are hypotheses out there as to why. There are probably cases where the synergistic interaction of two or more environmental challenges are actually destructive. So this kind of multiple environmental insult understanding is very limited. There are literally 3 papers in the literature that I know of in English that even address this, okay? So when we are pontificating about what microorganisms will do based on single strain laboratory information, we are cutting out a vast array of the information that we have not yet collected, but know must be out there to enable organisms to actually live in the natural environment. We also have a lot of trouble communicating with our physics and chemistry colleagues over whether or not organisms can take advantage of extremely transient events, and whether or not those transient events have to be simultaneous. So this came up a number of years ago when we were in a working group looking at reassessing the idea of Mars special regions. And the question came up over and over again, could organisms trap transient water that would happen at dawn, for example, when it condensed out of the atmosphere, and then hold on to that long enough until the temperatures, in some cases, for part of the year would get warm enough for them to actually use it. And the biologists pretty much came down on that, yeah, we think that might happen. And our physics and chemistry colleagues were absolutely not convinced. And we don't even know if that's true. We can't even say that that's true, but we have a sneaking suspicion that that might be the case. So what kind of planet are we talking about? For exoplanet studies, we really are focusing on something like ourselves because it's the only thing we are likely to be able to detect. And we are a very flamboyant and obvious biosphere. We are driven by sunlight and photosynthesis, and the critical zone, that is the area in which of the planet that includes the atmosphere and the surface and the nearby fluids, are mixing, and this is the critical zone. But if you look at the rest of the potential astrobiology targets in our solar system, they all belong to what I've started calling a planet type 2 biosphere, which means that they're not visible on the surface. They are not flamboyant. Gases in their atmospheres are in approximate chemical equilibrium, so there's no obvious biosignature of life in the atmosphere. And if they are being driven by energy, it has to come from in the interior, particularly in terms of the icy moons. Mars may be a relict biosphere, may have still organisms in the subsurface, but we have no idea. If they're still in the surface, their critical zone is therefore also bottom up because it would have to be relying on non-photon sources of energy. So besides the intrinsic value of this, it also applies to our understanding of exoplanets, because even though we could not detect these kinds of exoplanetary bodies, should they exist, if we find life in more than one place in our own solar system, then at least we have some scaling factor for contemplating this going into the future. I've added a third category recently, and this is because we have aspirations, some organizations like Breakthroughs, with their Starshot plans for eventually sending a physical probe to nearby planets. And I'm calling them Centauri planets just because those are the ones most under discussion, but there are a few other planets that are near enough that within the next century or two we may actually be able to visit. And this is something that we haven't really contemplated before. So I want to just leave you with the fact that of all the work that we've done in the subsurface over 25 years, there are significant similarities and properties that are not the chemistry. They are ecosystem-driven properties because organisms have to acquire stuff and use it, and acquire energy and use it. And this has led to probably a convergence of a lot of different properties. The ubiquity of using metal oxidation for energy. The ubiquity of growing in biofilms and mats. This is obligatory. The organisms do not hang out by themselves. This is really the functional unit of selection. Many times the organisms will not grow or prosper or do the kinds of interesting mineralogical transformations that we're interested in if you try to grow them individually. And so the individual way that we have classically looked at microbiology is really becoming antiquated in many ways. That microbial pioneer species invade bedrock, and they do it very, very effectively, and they do it in just about every kind of rock, and it doesn't have to go on in a cave, it can go on in fractures. We know that many of them are exceedingly slow growing. Many of them are regularly in what was hitherto thought of as very small cell sizes, but seems to be the typical cell size in these environments. This unusual preponderance of weird shapes that I already mentioned, and an enormously large biodiversity as we currently count it. We don't know how much of this matters evolutionarily or how much of this is actually incidental and because the subsurface is partitioned, but there are evolutionary lessons to be learned here. And that we have a lot of mineral reprecipitation by organisms and onto themselves. And this produces wonderful self-fossilization patterns that can be detected. So we have a range of problems still to solve within the whole realm of extremophiles. People have been working on them for a number of decades, but we have so many examples on this planet that there is much more to be mined, and I'll leave you with that thought. Bye-bye.
Questions for Penny?
Yeah.
I was wondering whether the newly discovered things by the Banfield group, the CPR and the DPAN, are they all subsurface? And if so, do they tell us anything about whether the closer we get to Luca, whether we get hyperthermophiles?
I'm not sure, Charlie. I mean, I think that in the realms that people working very, very deep are going, I think you might be able to argue that. What I secretly believe, or not so secretly believe, is that we really have a large number of indigenous microorganisms in the subsurface that have been there essentially forever, or for what amounts to forever.
But it's an important question because we'd like to know the origin of like whether it was in the subsurface or not.
You know, I think that the subsurface of life is, origin of life is plausible. I think that there are, energy sources that occurred in the subsurface. You dodged the bullet of having to worry about UV, very high intensity, short wavelength UV early on in the history of the biomolecules. How do you then export that life? I don't know. And I think that we underestimate the degree to which the rock fracture, now habitat, and the fluids on the planet interact. And they interact over a vast array of different geological timescales. And so I find it hard to divorce them as a single system, right? So I think the subsurface may have been a great place to kindle some of those processes. Whether we'll ever know probably will take finding life on another planet.
No.
Just to comment on that, John Sutherland, of course, argues that UV is directly involved in the origin of life and it provides the free energy. So
It's one way of getting energy, but it's not the only way of getting energy.
Right.
Right, so I mean, there are just so many sources. I also think it's, there's so much argument over the origins of life. Do you believe that the bag came first or the goo came first, you know? I tend to really come down on the side of some kind of enclosure. It could be mineral, but I think you need boundary condition in order to have life. And I don't care what you make it out of. You know, you can make it out of zeolites. You can make it out of, you know, other clay minerals.
Vesicles first, that's sometimes.
The what?
Vesicles.
Yeah, it's easy to cook up vesicles, but I gotta tell you, there are a lot of minerals that have cage structures. And they're already here, right? So how early a lot of those minerals got cooked up sort of depends on, you know, work by folks like Bob Hazen and his thinking about the mineral evolution on the planet over time.
Okay, any more questions?
No, thank you.
All right, let's thank Penny again.
Okay, so this actually, my introductory slide is showing the questions that Lynn alluded to earlier with the formalism about astrobiology is trying to understand the origin, distribution, and future of life in the universe. The reason I put this slide up here is because my first task when I started at the Ames Research Center in 1999 was to spend the first couple of months I was there walking around with Barry Blumberg, helping him set up the Astrobiology Institute. And I think we actually discussed this mural, which is on the wall of the biology building at Ames. And I regularly tell the story that this shows the origin, evolution, and just, you know, distribution and future of life in the universe. You have your free solar nebulae, you have condensation into planets, you have formation of life, and you have the evolution of astronomers who think they are the highest form of life in the universe. All the astronomers in the room can laugh or not. I think it was actually Barry who first made that joke to me. I was realizing that only as I was preparing this talk. And of course, I am currently talking about my previous job. I do not have my previous affiliation. I do not have my current affiliation on this slide. It's listed on the website, but I am here on my own time, so I am not talking on the basis of my current affiliation. My previous affiliation was NASA Planetary Protection Officer. I spent 12 years doing that, and this slide in the background is one of the slides that I would show, reminding people, if you want to find extraterrestrial life, you don't want to find Earth life. And unless you spend a lot of effort getting rid of the Earth life, you will bring it with you. There is life on Mars. We know this because we put it there. Is there a clicker or?
What kind of life is on Mars?
Earth life. There is microbial life on Mars because many of the spacecraft that we sent to Mars were not fully sterilized. They were carrying microbes with them, and the microbes did not die in the way. Oh, there we go, the other direction. Okay, so in the context of planetary protection, which I will go through the history later, and you'll see at the end of my talk why it is I structured the talk this way, the concerns that are being protected, the things that are being protected by planetary protection is understanding the distribution of life in our solar system. If all you're going to do is be an astronomer and look at stuff, but you don't touch it, it isn't possible to transfer Earth life to wherever it is you're looking at without touching. So anything outside of this solar system, unless you're actually doing a breakthrough starshot and trying to go there with a material object, does not fall under planetary protection. In addition, if there's somewhere in this solar system that you want to reach out and touch, and it doesn't provide a habitat either for Earth life or for potential native life, there are no restrictions on what you do. You have to tell people what you did because some future mission going to an object and finding gold and, you know, complex hydrocarbons and all kinds of interesting things might not realize that that was a crashed spacecraft, but you don't have, there are no restrictions on what you do. In some cases, there are objects in the solar system that might have habitats at a high enough level of concern that you have to maintain the capability to protect them if necessary. Galileo was crashed into Jupiter for this reason. Cassini was crashed into Saturn for this reason. Functional spacecraft discarded to protect objects that were discovered during the course of this mission. There are, of course, a few places in the solar system that we do believe provide habitats for native life, Mars, Europa, and Enceladus, and in those cases, there are restrictions on there are requirements for documentation, restrictions on operations to prevent the introduction of Earth life into those locations. And if you bring samples from those objects back to Earth, You have to contain them until you can demonstrate that whatever material those samples are composed of does not represent a biohazard. That is a replicating hazard that could get out and cause problems on Earth. So that's the context in which, that's the framework that guides all of the constraints that are imposed by planetary protection guidelines. And there's quite a lot of good reason for why things were set up this way. This slide is framed in the context of organic contamination, but we just heard an example of radio frequency contamination, where if you're trying to make a measurement saying something is present versus something is absent, your measurement will tell you something. The truth is also something. You have an option for life in fact to be present, or the object, the thing you're looking for in fact to be absent, and your measurement may say it's absent, your measurement may say it's present, and the matrix is you got a correct measurement, it really was absent, it really was absent, and your measurement said it was absent, that's a true negative. Good. If it's really present, and your measurement says it's present, that's also good. When you're talking about life on Mars, that's actually a really good day for science. Everybody who studies Mars to date, the Viking mission, the SAM instrument on the MSL mission, has been concerned about false positives. Viking announced that they saw a profile of, Viking announced that they saw chlorinated hydrocarbon from the Viking mass spec that was interpreted as cleaning fluid, despite having a positive result for the metabolism experiment. It was interpreted as air contamination. The SAM instrument on Mars Science Laboratory recently measured a whole bunch of Earth contamination, and they worked very hard taking samples from multiple places to identify a small number of ring compounds that were chlorinated that they could conclusively demonstrate, because they were present in some samples and absent from others, that those compounds were present on Mars. They were Mars organic compounds. They then went back, this is a group from Goddard, to the Viking mass spectrometer rod plots and identified those compounds in Viking. So Viking identified Mars organic compounds, and they interpreted it as Earth contamination. That may or may not be a false positive, but it certainly was a positive result that they thought was not there. They were avoiding false positives, and therefore they said an actual positive result was a measurement being absent. The measurement was absent. So they were up here, potentially. They were somewhere in there. Something is in fact present, and they interpreted their measurement as being absent. So people have worried about that. However, if you're worried about bringing material back to Earth, or about causing problems for humans in future colonizing Mars, if you're worried about having something that the consequences of our measurement, having a false positive is, oh, well, it was really there and we said it wasn't. So our scientific reputations are preserved because we didn't announce an incorrect result. If you're actually worried about the consequences, a false negative is way worse than a false positive. Because if you think something is not there and you stop taking precautions, and in fact it is there, that's a huge problem. And we know that's a problem from a whole bunch of history on Earth. So the way that planetary protection was framed, it started out in the 1950s, and I will get to that later in this talk, was recognizing that protecting things for science, that is preserving the ability to gain more information, also protects everything else we might subsequently want to do there at whatever location we're measuring on the basis of the prior slide. If you get the wrong information, you will make bad decisions going out into the future. So when, in the context of exploring Mars in particular, the discussions and the guidelines for planetary protection were framed in the context of a period of biological exploration, which in the 1960s was thought to be 50 years, and after 50 years we would know everything we could possibly want to know about the biology of Mars, and therefore then we could proceed to the subsequent use of whatever uses humans wanted to make of Mars. Planetary protection is not framed in the context of intrinsic value. It's a very pragmatic, it's not an ethical set of constraints. It was we might want to do things, we don't know enough yet to do them effectively, so we're going to learn more first. Very pragmatic. But even now, in the exploration of Mars, we are very close to the beginning. There's a whole lot we don't know about Mars. There's actually even more that we didn't know about Earth and don't know about Earth. So the constraints for planetary protection are framed in on the basis of the understanding that humans have many interests, understanding potential hazards supports making better decisions about all of them. So you take precautions early, and then you tailor your later constraints on the basis of what you have learned. So searching for Mars life or biohazards becomes more difficult every time additional Earth organisms are introduced. That was recognized from the very beginning. That's where the constraints on having organisms on spacecraft going to Mars came from. However, in addition, if you want to colonize Mars, and this is mentioned in a discussion recorded in the Space Studies Board, the WestTex report series. It was published by the Space Studies Board in 1959. This is a discussion at which Carl Sagan was present as a graduate student in as one of the members of this committee. And these discussions were taking place. In 1958, people were saying, if you send a spacecraft to Mars and it has dormant microorganisms on it, and then several hundred years later you try to terraform Mars, and you have Clostridium tetani on your spacecraft, and it wakes up, then every colonist on Mars will have to get vaccinated for tetanus. So sending Earth organisms, if Earth organisms are present on Mars, they're going to interact with the Mars environment and interact with the future human colonists in ways that could be potentially hazardous. I often have, well, when I was doing my previous job, I often had people saying, oh, well, as soon as Mars starts to get contaminated, we're just going to forget about it. My response to that is still, oh, so you stopped brushing your teeth after you ate your first candy bar? Earth organisms do cause problems. I've also had senior NASA managers tell me, oh, we know how to deal with Earth organisms, why should we worry about that? I mentioned this to a room full of epidemiologists and biosecurity people, and they all burst out laughing. Because it is not true. The guy 2 doors down from me had his mother die of a Clostridium infection in the hospital. We don't know how to deal with Earth organisms. Claiming that we do in the context of exploring Mars is just incorrect. So, and of course, we know this not just on the basis of recent information. We have millennia of history of Earth, on Earth, of humans moving things around and causing problems afterwards. This book, 1493, written by Charles Mann, he's a journalist, but he did a lot of very good research on the Columbian expansion, the beginning of humans transporting other organisms all around the planet. This is a textbook for planetary protection. This is why it makes sense to be careful, because so many times in the course of human history, we were not careful. And the introduction of malaria into Central America causes a $5 billion per year hit in 2010-ish dollars today. Since the 1500s until now, there is currently an economic hit of a very large scale on the basis of people not understanding that if they didn't introduce the Darcis organism, it wouldn't cause bad problems later. So it's a good idea to be careful and understand what you're doing. We were careful in the 1960s, of course, in the early 1970s, we had the Apollo program. They were quarantined. The quarantine was only released until after the Apollo measurements were done. There was a biohazard test protocol on Apollo program that measured the lunar route and came to a conclusion that they were not hazardous. If you know the scientific approach to that is questionable based on what we know now, but it was done. Allen Hale's meteorite, yes, we have Mars meteorites falling to Earth. We don't contain them because it's natural transfer, but understanding that this thing was a nanoscale bacterium, nobody thought bacteria could be that small before. Penny just mentioned we now are finding them everywhere because we realized we had to look for this stuff. If you don't look for it, you certainly won't find it. So it was over 6 years of international effort, part of the International Geophysical Year. That was the first time in human history that humans as a global community got together and discussed things that we would do on a global level. Planetary protection is actually the first time in human history that humans on a global level came together and said, yes, we're going to do this right. His first discussions were in 1956. That's before the launch of Sputnik, before they had the technological capability to do contamination of other planets. People at the international level decided it was a bad idea, let's be careful and only not take steps that we can't go back from. During the 50s and 60s, there was an extensive amount of discussion. After the mid-60s, at the UN level, everything was considered to be regular, sort of going along reasonably. In June of 2017, it was recognized, oh, with all this new stuff, maybe the UN ought to say something again. So UN COPOS reports to the General Assembly, except the report was accepted by the General Assembly. The committee also notes the longstanding role of COSPAR in maintaining planetary protection policy. COSPAR is the Committee on Space Research of the International Council for Science, and as a reference standard for spacefaring nations, a guide in compliance with Article 9 of the Outer Space Treaty. Article 9 of the Outer Space Treaty says that states party to the treaty shall conduct exploration so as to avoid the harmful contamination of celestial bodies and adverse changes to the environment of the Earth. The Committee on Space Research maintains guidelines. That all sounds very nice. However, thank you, Catherine, for this introduction. In 2007, the American Space Commerce for Enterprise Act was passed by the House. It's currently sitting in committee in the Senate. Guidelines promulgated by the Committee on Space Research may not be considered international obligations of the United States. In August of 2007, I was in office up until the summer. So in August of 2007, planet protection was moved. I was removed from office at the same time. In April of 2008, the newly hired planetary protection officer said, that's not just symbolic, it's really a change in the way we'll be operating. She was talking about the general framework of planetary protection at NASA. This was in a meeting of the the Mars Exploration Program Analysis Group, MPAG, and that was in the context of the February 6, 2018 SpaceX launch of a Tesla Roadster, where the trajectory that Elon Musk announced they would be launched was past Mars. It was only after somebody else in the literature said, wait a minute, you're not on the trajectory you said you were going to be on, that SpaceX said, oh yeah, we had a factor wrong in our calculations. They, in fact, were going exactly to the orbit of Mars. They only missed Mars by a few weeks. So in a report, in a comment from NASA Planetary Protection to the Space Studies Board in a review of planetary protection, they said, using limited trajectory information provided from SpaceX to NASA through the FAA, because it's a commercial launch, to calculate the propagation of the orbit trajectory, primarily to assess immediate potential risks. The trajectories could not be rendered into standard probability of impact calculations to assess long-term risk to scientific assets beyond the immediate launch window. That means this was not done according to the guidelines, and apparently the guidelines may not be considered US obligation. And just to remind people, I am at this meeting on my own time. Thank you.
You mentioned at the beginning that Mars has already been contaminated. Can you cite what is it based on?
The only spacecraft that were fully sterilized were the Soviet landers, to the extent they stuck them next to huge radiation devices, and they reported to COSPAR that they had been sterilized, and Viking 1 and 2. The landers since Viking, Pathfinder, Mars Exploration Rover, Mars Polar Lander, which crashed, and contributed some millions of organisms to the surface of Mars that is in a broken open state, not enclosed inside the hardware, plus Mars Science Laboratory, Phoenix, had a small number of organisms, but they all included live organisms. The ESA lander, Beagle, was sterilized, but not, they did a pseudo-sterile assembly, and then of course the ExoMars lander, ExoMars test case.
What about Insight?
Insight, same way.
That drilled in probably,
yes,
put microbes into the surface.
Well, they actually did Insight did a really good job. They did a very careful assessment of the surface where they were going to show that it really would not have good level of habitat. No, Insight did a great job. Yes.
Cassie, if I remember correctly, it's actually not technically called sterilization. It's called bioload reduction.
Yes.
And, in case people in this audience don't know, they only look for one indicator species.
No, that is not correct. We look for things that can grow under certain culture conditions.
Aerobically.
Yes, there is a certain set of culture conditions that is used as the standard assay. That is fully well understood to not be a catalog of organisms.
No.
That assay is based on the Viking sterilization. It was looking for heat-resistant things because Viking killed everything with heat.
Only aerobically on TSA plates. They would miss Clostridium.
Yes, it would miss all kinds of things, but that's known.
Yeah.
It's an assay. It's a proxy. It is not intended to be.
The other thing is that sterilization is not clean. And although they make an attempt to clean it. It's not necessarily 100% clean and free of organic material.
Well, you're sending plastic on the spacecraft, so of course not. I mean, the point is, the Vikings did both. The Viking mass spec was very carefully cleaned with hot gas, as well as baked. So there is definitely a synergism or a conflict, depending on how you look at it, between having dead organisms and having no organics. But that's a technological challenge, but it has been achieved, yes.
Yeah, I think you said that there were biohazard tests done before the Apollo 11 astronauts were let out. What does that mean? Were they tests on mice or chimps or something?
So there was a protocol that was developed by Emory University on the basis of a lot of the biomedical testing. It's been published somewhere. There was the lunar sample material, the samples, not the astronauts themselves.
Did they use like mice?
Yes, yeah, there were chemical tests and feeding experiments. They grew plants in it. The whole series of tests. It's on the NASA Technical Report Server archive. I mean, it is published. It's a little difficult to find. I think the History Office may also have some information.
And then 3 days to do it all, and then...
No, 3 weeks.
3 weeks? They stayed in quarantine 3 weeks?
They were in quarantine for 3 weeks,
man.
which you were next, then Ellen, then.
So do you know how much natural contamination there is on Mars from Earth due to panspermia?
There have been calculations. Jay Melosh has done a number of those calculations. The big difference is that it takes a long time to get there. So it's even thousands of years in the space environment, depending on how large the material, the objects are, is going to have a lot more of a lethal effect than 2 years inside a nice warm spacecraft.
Yeah, just another anecdote. In the summer of 1976, when the Viking landers came down, JPL had a big celebration of the landings in the Von Karman Auditorium, and they invited Ray Bradbury, and this famous science fiction writer, to talk about that. And
Sure.
Ray Bradbury starts off his talk by saying, "Is there life on Mars? Yes, there's life. It is us." Of course, it was human beings spiritually, not in terms of microbes.
Every spacecraft we have sent to Mars has found signs of intelligent life on Mars, because every spacecraft we have sent to Mars has taken pictures of spacecraft. We know that it's not Mars spacecraft. But that's a contamination thing. We recognize that contamination. We won't necessarily recognize all contamination. You had a question, and you. Oh, sorry, did I miss? Were you before? I'm sorry. Did you put up your hand before?
I've had it for a while.
Okay, I didn't see you. Is it okay if I let him go first?
Yeah. Just to connect to something that came up in Penny's talk about Starshot. To my understanding, NASA's been charged by Congress to send out a Starshot mission by 2060 or something. And do you see any reason to seriously entertain planetary protection considerations for that kind of mission? So I can tell you, I know of 2 papers about it.
I have actually had several conversations. The constraints for planetary protection are based on an acceptable risk model. The risk considered to be acceptable was a contamination probability of 1 in 1,000 per mission, if I remember correctly. And it was modified for Europa and Enceladus to be just 1 in 1,000 in general, 1 times 10 to the 4. So given the size of the spacecraft and the size of the solar system, I would expect it as a lower probability that any object in that solar system is going to be contaminated by something sent from Earth. If you send a whole bunch of them, you might change your calculations. But there is a probabilistic risk assessment, risk-benefit analysis that is embedded from the very beginning of planetary protection constraints. So that can be applied to other locations. Now,
would you just say once again, what were the conditions that the FAA imposed on Elon Musk's?
There were none.
None at all. Does the FAA think it has authority to do that?
In my former role, I provided a list of information that should be requested from spacecraft that might go near Mars.
Have the FAA responded?
I was removed from office before I got an answer.
I'd like to talk to you some more about it.
That sounds good. Next, I'll have time for one more. Ellen, it was you. No, I did this. I think it was you. I'm sorry.
Well, I had a related question about what exactly, assuming we agree to abide by the treaty, whether...
It's not just a treaty, it's a good idea.
Okay, good. But what restrictions does that obligate us as a country doing spacefaring experiments? as opposed to regulating our private companies who have now chosen to do space?
So Article 6 of Article 2, the Outer Space Treaty addresses, it makes it clear that states party to the treaty are responsible for the actions of their non-governmental entities. That means also states party to the treaty ought to have state national laws. The only national law in the US that addresses any kind of this is the constitutional statement that treaties are the highest law of the land. Many other countries have national laws. The Soviet Union had a national law on planetary protection, which carried over into Russia. The US does not.
I'm just trying to digest the implications of your final slide.
Maybe we should talk about that offline. You're welcome to have a conversation in the group, but I will.
Yeah, I mean, I'd be interested in, I mean, you can just say I don't want to talk about
Well, we have a
except for
panel.
online, but I mean, the question I was going to ask is NASA abandoning planetary protection?
I can't speak to that. I don't have the rope job anymore.
I can say something small to that. On the missions that I've been part of that have been proposed in the recent few months, everybody is required to submit a planetary protection contribution for each mission proposal.
That has always been good. The question is who's reviewing it.
I don't know who's reviewing it. I can't answer. I can say, but it's still required as part of the mission proposal process, as well as
I've had to do those
through
too.
phase A, B, C.
I'm just trying to read the tea leaves about what's happening, what direction is being taken here.
I think there still is awareness within NASA that activities have the potential to interfere with future NASA objectives. If you're talking about something like planetary resources that has no scientific objective.
All right, let's thank Cassie again. And